The topic for today's lecture is CMOS inverter operation and description. In the previous lectures, we have studied about what is meant by CMOS and how it operates. But apart from that one, we will be seeing about CMOS inverter. We are supposed to understand what are the 5 different regions of operation. It means that whenever a CMOS is trying to convert a logic 0 to 1 or logic 1 to 0, the CMOS inverter has to go through all these 5 regions of operation. Until it doesn't go through these 5 regions of operation, we cannot expect that the working condition of CMOS will be producing as an output depending upon the input. It means the working condition, the procedure in order to output an input, the CMOS will be following this will be going through these 5 regions of operation. So in this lecture, we'll be trying to study about what are those 5 regions of operations of CMOS inverter. And later after that one, we'll be looking forward for some another topics related to the VLSI, such as like what is meant by power dissipation, what are the different kinds of power dissipations are there, and transmission gates, what is meant by transmission gate, and what is the tri-state inverters. So first, let us look into this. Today's topic, that is CMOS inverter operation and description. As we all know that this particular circuit denotes the CMOS inverter circuit, where it will be having PMOS has a pull-up device and NMOS as a pull-down device. It means that the device which is connected to the VDD, we call it as a pull-up over here, and the device which is connected. Device means I'm talking that with respect to the MOSFET. Here, whatever the device I'm terming, it means it is a transistor. Here, the P transistor is a pull-up device and the N transistor is a pull-down device. Now, we can see the construction part. In the construction part, you can see that both the gate terminals of the PMOS and NMOS are connected, are shorted, and to that particular shorted gate, VIN has been supplied. In the similar way, at the output, both the drain terminals have been shorted, and to the shorted drain terminal, output terminal has been connected. And apart from this one, you can see the source of PMOS is connected to VDD and the source of NMOS is connected to ground terminal. And we all know that CMOS structure or a MOSFET. MOSFET is not an 3-terminal device like BJT, but it has got 4 terminals, like what is meant by source, what is drain, what is gate, and apart from that one, it has a 4th terminal which is called as a bulk terminal or the body terminal or the substrate. We call this other different names for the 4th terminal: body, substrate, or bulk. So this is that 4th one. This is a bulk terminal or substrate or body, and you can see here this is again the substrate part of the bulk of this NMOS, and this is a bulk of the PMOS. Now, how to connect the bulk terminal of a MOSFET? The bulk of PMOS should always be connected to the VDD. It means that blindly you try to understand that the bulk is always connected to the source of that particular transistor. For the PMOS, we know that the source is connected in the upward direction, so the bulk is connected to the source in the upward direction. In the similar way, the bulk of NMOS is connected to the source of the NMOS, to the source of NMOS. So that's why we are connecting the bulk in the downward direction to the ground terminal. So always keep in your mind the bulk terminals have been connected to the source terminals of that particular transistor. So now, because this particular transistor, this particular structure will be working such a way that one will be turning on in one phase of the operation and another transistor will be turning on in another phase of operation. Because of this kind of operative phases, this particular configuration is known as a complementary MOSFET configuration. That's why it's called as a complementary MOSFET configuration, because here NMOS and PMOS transistor work as a driver transistor, where one transistor is on in one phase and other transistor is off in another phase. So it goes on repeating. Only for the one phase of a transistor operation, only one transistor will be on and other transistor will be off. So it is like from phase to phase, the transistor operations or the turning on of the transistors will be changing. Because of that reason, this is called as this kind of construction where logic is been implemented by using both the PMOS and NMOS is called as a complementary MOSFET configuration. And we all know that the input is connected to shorted gate and the output is connected to shorted drain, and the bulk is connected to the source of the two transistors. So this is the main operation or main constructional part of the CMOS structure. So see now, these are the basic important voltages which you are supposed to understand and which you are supposed to remember in order to construct any kind of MOSFET or CMOS configuration structures. First one, whenever the voltage between the substrate biasing, it means VSB is nothing else but substrate bias voltage. It's a substrate voltage whenever it is equal to 0 for both the transistor. These are the condition. The voltage between the gate and source of N transistor will be always equal to V in, and the voltage between the drain and source of N transistor will be equal to V out. And similarly, for the PMOS also, it is like the voltage between gate and source of P transistor will be V in minus VDD, and here it is voltage between drain and source of PMOS will be V out minus VDD. See here, in fact, both these equations are same. In fact, both the equations are similar, and it's all, I can tell that both are like 100% they are same. Why? Because the same equations, if you just interchange P and N here for this PMOS, if you interchange N and you can even put N over here, this equation becomes this one. Why? Because here, whatever the VDD is connected, it is minus source voltage. What are the minus source voltage? For PMOS, the source voltage is equal to VDD. So we have put it here, the voltage between the gate and source, that is VGS, is equal to V in minus VDD. In the similar way here, if you go to the NMOS, here the VGS for NMOS also will be equal to V in minus the source voltage. But what is the source voltage for the NMOS structure? The source voltage for the NMOS structure is equal to ground terminal, that is equal to 0 volts. So that's why it is V in minus 0. V in minus 0 is nothing else but ultimately it is again V in only. So that's why I have told that this both equations are same. Even for the VDS of PMOS is equal to V out minus VDD. And if you apply the same kind of equation for the NMOS, it will be VDS of NMOS equal to V out minus ground terminal. Ground is equal to 0 volts, so it is ultimately it becomes V out only. So these are the conditions and equations for the voltages of PMOS and NMOS with respect to drain and gate terminals. Now next one, let us see about the current, how the current is varying over here. Whenever the input voltage which is supplied to the transistor, if it is supplied to the transistor, if it is very less than threshold voltage, we know the threshold voltage will be somewhere near around 0.4 to 0.6 volts. So now if your input voltage is supplied through to the NMOS is very lesser than this one, means lesser than 0.4, then what happens? Your NMOS will not be turning on. Why does the NMOS doesn't turn on? Because we know that the NMOS will be turned on only whenever the logic is equal to 1. There is logic voltage, logic input is equal to 1, it will be turned on. If it doesn't turn on, if it is a logic input is not equal to 1, what happens? The NMOS will be off. That situation only we call it as a cutoff region. The cutoff region is nothing else but whenever a transistor is in the off state. Whenever, if the input of the NMOS is smaller than the threshold voltage, then the NMOS will be in the off state. If NMOS is in the off state, what happens to the PMOS? PMOS will be in the working state. It is in the turned on state. That turned on state of the PMOS, we call it as a linear region. Linear region is the region where the transistor will be in the on state or in the working phase, and cutoff region is a region where the transistor is completely in the off state. It is not in the working state. So the drain current for the transistors is equal to 0. So ultimately the drain current will be equal to 0. Why? Because your complete transistor is not working. So that's why the drain currents of both the transistors will be 0. So ultimately the drain current of NMOS and the drain current of PMOS will be equal to 0. Drain current of NMOS and drain current of PMOS is equal to 0. Therefore, the output voltage, VOH means here.
Sir.
Yeah.
Sir, once explain the before point, sir, when the input of NMOS is smaller than threshold.
Yeah, fine. See now, Whenever the input of NMOS is smaller than the threshold voltage is what? It is the minimum voltage to turn on the transistor. Means until and unless you don't supply the minimum voltage, your transistor will not be turning on. So what is the value for the threshold voltage as per the technologies? You might be aware about different kinds of technologies like
0.4 to 0.6.
yeah, 0.4 to 0.6. So now here the minimum voltage that is 0.4 to 0.6 depending upon the technologies. If you don't supply that minimum voltage to the input of the NMOS, it means whenever the input of NMOS is smaller than the threshold voltage, your NMOS will not be turned on. Why? Because your NMOS will be turning on only at the logic 1 state. Whenever the input is logic high, then only NMOS will be turning on. So now whenever it's NMOS is not turned on, means it is not in the working state. It is completely off. The transistor is off. That off state of a transistor is called as a cutoff region. It is called as a cutoff region. And whenever the NMOS is off, we have seen in the previous slides that this kind of structures or configuration is called as a complementary configuration, complementary MOSFET. Why do we call it as complementary MOSFET? Because for one phase of a transistor, one phase, one transistor will be in on state, other transistor will be in the off state. So similarly, it is happening here. Whenever the NMOS is in the off state, the PMOS will be in the on state. That on state of the PMOS is called as a linear region operation. If a transistor is working, means it is called as a linear region. If a transistor is off, means it is called as a cutoff region. And regarding this linear region, cutoff region, and saturation region, the other one, for linear region, we have studied as non-saturation region in the previous lectures. You can even go for the, you can look into the lectures like basic electrical properties of MOSFET. In that one, I have explained in detail about what is cutoff region, what is a linear region, and what is saturation region. So this is regarding linear and cutoff region. Now coming to the drain currents. Whenever the transistor is in the off state, definitely the linear region, definitely the transistor will not be working. It means that the electrons will not be moving across the channel. That's why what happens, the drain current also is going to be 0. So that's why the drain current, ID is the drain current is going to be 0. In now similarly, if you look at the output voltage here, therefore the output voltage is VOH. VOH means what? It is a high logic at the output. VOH means high logic at the output voltage. That is called as an VOH. The output voltage is equal to the supply voltage. Therefore, whenever this condition occurs, at that time the output voltage is equal to VOH, and that is equal to VDD. See now here, whenever the NMOS is off, then definitely the PMOS will be on. Whenever the PMOS is on, what happens? The VDD will flow through the channel, and that VDD will be stored in the output capacitance. That's why we say that our output is equal to, we have got some output, our output is obtained. That output is nothing else but here, Vout is equal to VDD. Whenever this state happens, whenever the NMOS is off, PMOS will be on. If PMOS is on, definitely the VDD will flow through the channel, and that VDD is stored in the capacitance of the output, and that output is nothing else but Vout equal to VOH. That's a high output voltage, that is equal to VDD. It is not exactly equal to VDD, but it will be minus some part of minus of the VDD. Now let us see the another situation similar to the previous one. Now let us see what happens if the input voltage is greater than VDD plus threshold voltage. Whenever the input voltage is greater than VDD plus the threshold voltage, then the PMOS transistor is in the cutoff region and NMOS will be in the linear region. If VDD is supplied, see these are the conditions which are very important. We are supposed to understand and remember it. Whenever you supply a input voltage which is greater than the VDD plus threshold voltage, it means that if you're supplying something like around 5 volts is your VDD and threshold voltage is 0.5 or 0.6, it means if you're supplying 5.6 volts as an input at the PMOS terminal, then definitely your PMOS will be turned off. It enters into completely cutoff region. We know that the PMOS will be working only at logic 0. But here what you're doing, you're supplying a voltage which is greater than that logic 0. That is logic, it is much greater than logic 1. Or logic 1 is only VDD as per our considerations. VDD will be logic 1 and logic 0 will be ground terminal. But here we are supplying more than the logic 1. Whenever you supply this kind of voltage as an input voltage to the PMOS will enter into cutoff region, And whereas coming to the NMOS region, the NMOS transistor, it will be in the linear region, that is operation. It will be in the operative region. Therefore, if this is the state, now let us see the drain currents. Here in this situation also, in the initial phases, the drain currents of these two transistors will be is equal to zero state only. It will be equal to zero. And similarly, coming to the what is that output? With the output voltage, whenever the NMOS is on and PMOS is off, then the output voltage, that is VOL, is nothing else but low output voltage, low logic state, low logic at output of the voltage, that is V out equal to zero. Why does the output is equal to zero even though the NMOS is on here? Even though the NMOS is on, in this state, the output is becoming equal to zero, because whenever the N transistor is on, there is a direct connectivity between the output terminal and the source of the NMOS. So what happens? Gradually, the charge will get discharged through the channel of the NMOS, and ultimately, whenever the capacitor which is connected to the output of the CMOS is completely discharged, then definitely what you say, your output of that complete CMOS structure, that CMOS inverter, will be equal to zero. So that's the reason how you get output is equal to zero. It means in the previous state, some particular input has been stored at the output, and that output is gradually discharged because there is a channel has been created in the NMOS structure. Through that channel, the charges will discharge gradually. Why? Because a potential gradient has been taken place. What is this potential gradient? We are having a higher potential at the output and lower potential at the ground terminal of the NMOS. Because of this difference in the potentials at the output and ground of the NMOS, what happens? The charges move from high potential area to low potential area, and ultimately will not be having any output because of the gradual shifting of the charges from high potential area to the low potential area. Ultimately, the output is V out is equal to be zero. Now, up to now, we have seen about what happens to the NMOS and PMOS with respect to cutoff region and linear region, that is non-saturation region. Now, let us see what happens to the devices whenever it is in the saturation region. The NMOS operates in the saturation region if Vin is greater than threshold voltage, and if that is the case, then these are the conditions for the saturation region. If you want to be an VLSI engineer, definitely these are the most important equations for any of the VLSI engineer to remember, because definitely while constructing or while designing any kind of CMOS structure, every time a VLSI engineer has to be aware about whether the particular transistor which has been designed before going for the outputting of that particular module, definitely he has to look that each and every transistor is in the saturation region or not. So for saturation region, he has to remember these conditions. He has to make manually, he should make the mathematical analysis, and he should check whether the conditions have been obtained or not. So for the NMOS transistor, if it is working in a saturation region, the condition is that the Vin should be greater than VTO, that is a threshold voltage. If it is greater than threshold voltage, then the following conditions will be satisfied. What are the conditions? The drain source voltage of NMOS will be always greater than or equal to gate source of voltage of NMOS minus threshold voltage. So your voltage, whatever the voltage you have got over here, that voltage should be greater than this particular difference. That is a gate and source voltage minus the threshold voltage which you supply to that particular device, that is NMOS, with respect to the technology which you are using. Depending upon the technology, this threshold voltage will be changing. So you should make a change of that one here, and you should look whether this condition is satisfied or not. Similarly, for the output voltage, what happens? The output voltage has to be always greater than Vin minus the threshold voltage. So these are the conditions for the NMOS transistor. In the similar way, for the PMOS transistor, if a PMOS is operating in a saturation region, means here your Vin is lesser than VDD plus this one. What is this one? VTO. Why we are talking about Vin is always lesser than VDD plus VTO, that is a threshold voltage, because whenever the Vin is greater than this equation, VDD plus VTO, your PMOS will enter into the cutoff region. So that's what we have seen in this first condition here. Whenever the VDD is whenever the Vin is greater than this VDD plus VTO, your PMOS will enter into the cutoff region. So that's why if your transistor is in the on state and if it has reached to the saturation region. Saturation region means what? We have studied in the basic electrical properties that a complete pinch off of the channel takes place. Pinching of the channel will be taking place. So whenever the pinching of channel takes place, your MOSFET, any MOSFET, either NMOS or PMOS, will enter into the saturation region. Further saturation region, these are the conditions in order to remember for both PMOS and NMOS. Now, coming to the core part of this particular lecture, our main aim of studying this particular lecture is that in order to understand the different input logics and different phases and different regions of a particular NMOS inverter. See, at this NMOS inverter will be always going through the phase of this 5 regions of operation, whether it is an CMOS structure or it is a it's a CMOS inverter. I'm not talking about the NMOS inverter. I'm talking about CMOS inverter. For the CMOS inverter, your inverter will be going through these 5 regions of operation in order to output any of the input. So see now, for different values of input voltages, the operating regions are listed below for the transistor. Region A, whenever it is region A, for the region A, the condition is that your input should be always lesser than threshold voltage. Input should be always lesser than threshold voltage. Whenever it is a threshold voltage, then what happens? The output will be high voltage will be obtained. The high voltage is obtained. It means what? Whenever you are supplying 0 as a logic to the input to the gate of the particular CMOS inverter, your particular output will be VOH. Why does the output is VOH? Your PMOS is turned on and NMOS will be turned off whenever the input is equal to 0. Whenever input is equal to 0, Vin is equal to 0, the PMOS is turned on. That's why we have written here it is a linear region. And NMOS is turned off, it means that your NMOS has entered into a cutoff region. Whenever this state occurs, what happens? The channel of the PMOS is developed, and through that particular channel, the VDD flows through the output. Whenever the VDD flows to the output, we say we have obtained some output. That output will be high logic at the output of the particular transistor. That's why we have written it as VOH. And similarly, coming to the second region. In the second region, whenever your input is equal to low input logic, whenever your particular this transistor, whenever this input is equal to low input logic, then what happens? If this is the case, then your output will be almost high. Your output is almost high. Why? Because your both the transistors will be in one, NMOS will be in saturation region. It means your NMOS has got completely pinched off, and you cannot expect any kind of operation in the NMOS. It is completely in the saturation. But whereas the PMOS is still in the working state, if it is in the working state, means a channel is still there. Here in this case, saturation region means what? Your channel is completely pinched off. Means there is no exit for the charges to move from source to drain. The channel is completely closed at the drain, so there is no exit for the charges to move. But whereas here in this region, there is some exit for the charges to go from source to drain. So that's why your PMOS is in the on state. Whenever it is in the on state, then definitely what happens? The VDD flows through the output. Whenever the VDD flows through the output, you get a maximum output voltage. That is called as VOH. So that's why your output will be always equal to high state. Coming to this one, third phase of region of operation. Anyway, in next slides, you will study much more detail about these operations, but I'm trying to give you the glimpse of these operations now here itself. So see now, whenever we comes to the region 5 operation, whenever it is region 5, your input voltage will be almost equal to threshold voltage. Whenever its input voltage is almost equal to threshold voltage, your output also will be that is equal to threshold voltage only. Whatever you supply over here as an 0.4 or 0.6, your output also will be in same thing. Whatever you supply at input, if that is the case, then both the transistors are in the saturation region. See, this kind of condition, the region C condition, we can call it as an buffer state. It's a buffer state. Buffer state, why do we call it as a buffer state? Because buffer is nothing else but it's a cascading of 2 inverters. It's a cascading of 2 inverters. We have even studied CMOS buffer in the previous lectures. Whatever you supply as an input, the same will be outputted at the output part of the construction. So it's a cascading of 2 inverters. So here also the same thing is happening in the C region. if input is equal to threshold voltage, whatever the voltage you supply here, the same output you're getting. So that's why we can call it as a buffer state. And in this region, both the NMOS and PMOS will be in the saturation region. These are very important objective parts with respect to any kind of competitive exams. They might even ask what is the state of operation for any of the transistor in region A or region B or region C. So now you should be in a position to remember and answer that particular questions. Like if it is in region C, NMOS and PMOS will be both in saturation region. If it is region A, the NMOS will be in cutoff region and PMOS will be in linear region. So these are important objective questions. Coming to the next one, region D. In the region D, what you're supplying? You're supplying your input equal to high input voltage you're supplying. Whenever it's a high input voltage, definitely what happens? The PMOS is going to turn off, and NMOS is going to turn on. Whenever it's NMOS is turning on, we have seen in the previous slide that if NMOS is turned on, what happens? Whatever the output is stored at the capacitor, that complete output will be discharged to the ground. Whenever it is completely discharged, your output will be low. Your output is equal to low, that is VOL. And if this is the case, by the working condition of the transistors, we can say that if NMOS is working over here, the NMOS is in the linear region. If PMOS is not working, that's PMOS is completely, it is not exiting any kind of charges. So we can say that the PMOS is in the saturation region. Now coming to the last region of operation, that is region E. In the region E, whenever you supply a voltage, which is input is greater than VDD plus VTO. Whenever the input is greater than VDD plus VTO, we have seen in the previous slides, your PMOS will be completely turned off. If a PMOS is completely turned off, it will be in the cutoff region. And since your supplied some input is much greater than VDD, it is almost equal to logic 1. If it is a input is equal to logic 1, your NMOS will be turned on, and NMOS is turned on means it is in the working state. So that's why we can say your NMOS is in the linear state of operation. If your NMOS is in the linear state of operation, just look at this output parts. Whenever NMOS is working, then only the output is going to become 0. That means output is going to become low because of the discharging of the charges. And this is a graph for this operations whichever I discussed just now. This is the region A, that is in between 0 and threshold voltage. Then again region B, region C. In this region C, you can see now both are in the saturation region. Both the transistors are in saturation region. NMOS and PMOS both are in saturation region. That's why it's denoted as this one. Both are in saturation region. And coming to the D region, in the D region, what happens? Your PMOS will be in saturation and NMOS is in the linear region. And coming to this one here, the PMOS will be off, and whatever the NMOS will be in the linear region. So this is the complete diagram. And in the second half of this particular syllabus of the unit, always remember there are two important questions, and the most priority has to be given to this particular topic, CMOS inverter. If this question has been asked in your university papers, you should explain in detail about all these regions. And if you draw this diagram, definitely you're going to secure the complete full awarded marks. Now let us see these operations. Whatever I explained now, I'm trying to detail it now again here. In the region E, in the region 1, what happens in the region 1? Your input is equal to logic 0. If input is equal to logic 0, the PMOS is turned on and NMOS is turned up. The same entire operation I have given over here. If a PMOS is turned on and NMOS is turned off, then definitely the output is going to become what happens? VDD. The output will become VDD. You're going to get some output. So that output we call it as a logic 1. Now coming to the region 5. In the region 5, corresponding to the output corresponding to region 5, whenever the input equal to logic 1. If input equal to logic 1, what happens now? If the input is in logic 1, the NMOS will be turned on and PMOS is turned off. If that is the case, then definitely what happens? The current flow through the circuit. The current will be flowing through the circuit. It means that here in the region 5, we have seen region 5 means region E. It is A, B, C, D, E. That's in the region 5, the PMOS will be cut off and NMOS will be in the region linear region. And these two regions are like Region 1 and region 5 are static conditions. These are the static state of operation of this PMOS and NMOS. Coming to the next one, in the region 2. In the region 2, what is happening? The input voltage has now increased. It has increased to the next level. So that's why that is above the threshold voltage. Whenever it is above the threshold voltage, what happens? The NMOS transistor will be conducting, and because of that one, your NMOS transistor, after conducting for some amount of time, ultimately it enters into the saturation region. Coming to this one, the PMOS is also conducting, but with a small voltage difference between its drain and source. This PMOS will be in linear region. Unsaturated region means it will be in the linear region. This is the state of operation for the region 2 for NMOS and PMOS. In region 4, we have seen in what happens in the region 4. The conditions are similar to the region 2, but here the roles will be reversed. The roles are reversed here. It means that you're completely, we can see that the PMOS has a large voltage across it, while the NMOS has a small voltage drop. So it is a exactly the opposite state of this regions. We can see it now. Region 2 and region 4. In the region 2, the NMOS is in saturation and PMOS is in linear. Coming to region 4, NMOS becomes linear and enters linear, and PMOS will enter into the saturation region. That's why here in the region 2 and region 4 are exactly reverse conditions. This is what happens in the region 2 and region 4. Coming to the region 3, the switching of this operation takes place, and the region 3, what happens? Both the transistors will be in saturation region. Both the transistors are saturation. That's why most of the energy consumed in the switching from one state to another state is attributed to the large current flow that happens whenever it is completely saturated. So these are the conditions now here. Since both the transistors are in series, the current flows through them is same, and we can write our equation as current at the drain and source of PMOS is equal to minus of drain and source of NMOS. We are trying to notate this one minus because it is an opposite of PMOS and NMOS in order to identify that one transistor is sending the holes, another transistor is sending the electrons. That's only the reason why we have put it here negative. But ultimately, both the currents will be same. One is a current due to the holes, and another one is current due to the electrons. There is a positive charges and negative charges. And these equations we have seen in the basic electrical properties. The IDS of the PMOS, the drain current of the PMOS will be equal to this particular equation. And similarly, coming to the drain current of this NMOS is going to be this one. And finally, the equation, writing this equation, if you put these equations and if you solve for the input voltage, the input voltage of this transistors will be V input of PMOS plus VDD plus threshold voltage of the beta factors divided by 1 plus of this particular beta factors. And this is the current source situation. This is a source situation whenever both the transistors are in saturation. Always remember, whenever both the transistors are in saturation, your transistors will be acting as a current source elements. Current source means it will be sourcing some current. So this is the diagram, equivalent diagram for the region 5. In the region 5, both the transistors will be in saturation. Therefore, they act as a sources which are shown here. It means that both the transistors are acting as a current source. And even this one is an important objective question. In the region 5, if in the region 3, if both the transistors are in saturation, both the transistors are acting as a current source elements. And these are the equations regarding that region 3. Whenever it is in the saturation region, both the transistors are acting as current sources, and these are the conditions for the input voltage and output voltage. And this is a very important part where you're supposed to understand W/L ratios of both the transistors. Both here, it means that from this particular equation, we can say that whenever your transistors are in a saturation region, you should even look after about the W/L ratio. What is the width of the transistor and what is the length of the transistor? Both the width and length of the transistors will be same. It is almost equal to same. That's why the mobility of electrons and holes are inherently unequal. So these are the conditions for the PMOS and NMOS. Now coming to the next part of this lecture, that is a CMOS inverter. And this is also another important question. If you don't expect a CMOS inverter as a question in your final paper, definitely you can expect BiCMOS inverter as an question in your final university question paper. And this is also another important design. Why do we need to study about BiCMOS structures? Because the main disadvantage of the CMOS technology is that CMOS technology is really good at consuming lower power and lower power and smaller size and all these other advantages of the CMOS structures. But when we come to the switching speed, when we come to the switching of the CMOS structure, the switching is not that good as the BJTs are meant to do. But when we have seen that in the BJT, the switching will be very good, and the switching means I'm talking about the passing of the signal at the output. It has to drive a large amount of loads at the output. That switching speed is not good with respect to CMOS. So that's why what they have done, the researchers has worked in order to combine both the CMOS structure and also by a BJT structure, whereas your the input part of the entire model will be designed with the help of CMOS, and only the output will be designed with respect to BJT. And this kind of structures we call as a BiCMOS structures. And now here in this particular lecture, we'll be studying about BiCMOS inverters. Means an inverter is been designed here with respect to CMOS technology and also BJT technology. So let us see now BiCMOS inverters. You can see now. See, this is the input part. This is the input part where it is being designed with respect to the CMOS technology, and this is the output part which is designed with respect to BJT technology. Since you are having both the technologies in one design, we call it as a BiCMOS structure. Whenever you have got both the technologies as a one particular design, we call it as a BiCMOS structure if you are using CMOS and BJT. So let us see now the operation of this one. The very approach of this BiCMOS is to exploit the advantages, characteristics of the bipolar and also CMOS technology. What are the advantages? The CMOS will be having low power consumption part, and also the smaller size is a advantage of CMOS. And coming to this BJT, it is having very good driving capability. It can drive very good output loads. So that's the main important thing as an advantageous part. Hence, in BiCMOS design, the rational approach is to use the MOS switches to perform the logic functions. This is a logic function where the MOSFET has been used, and bipolar transistor is to drive the output part. The bipolar transistor is mainly used to drive the output loads. The basic element here is that the inverter and the simple BiCMOS inverter can be imagined just like the one which is shown here. This is a simple BiCMOS inverter where you are having the input structure has been designed with the CMOS structure and output structure has been designed with the bipolar transistors. T1 and T2 are the bipolar transistors, and T3 and T4 are the MOSFET transistors. So now let us see the operation of this one. The inverter circuit consists of two bipolar transistors, that is T1 and T2, and one NMOS transistor T3 and one PMOS transistor T4. Both the MOS devices will act as an enhancement mode devices here. Both are in the enhancement mode means what? You are supposed to supply some input in order to create a channel first. So both are in the enhancement mode transistor, and the functioning of this BiCMOS inverter is just as below, which is given over here. Whenever you supply some input, Vin is equal to logic 0. If Vin is equal to logic 0, that is 0 volts is been supplied, then definitely what happens, the PMOS, that is NMOS, will be turned off and PMOS will be turned on. So now here turned off. Now what happens to this one? That PMOS is turned on. Because of the PMOS is turned on, you can see, and now whenever the NMOS is turned on, what happens to this one? T1. T1 is what? It's a BJT1. The BJT1 will be going into non-conducting state, and if the NMOS is turned on, the supplies the base current to the T2. You can see here now. If the NMOS is turned on here, if NMOS is turned off, what happens? The drain of this NMOS, the source of the NMOS is connected to T1. If it is connected to T1, what happens? The T1, it is not supplying any kind of input over here to the T1. Your T1 goes into off state. It becomes non-conducting transistor. That's non-conducting BJT. Similarly here, whenever the T4 is on, that the PMOS is on, definitely what happens? The channel is formed and the VDD flows through the output of this one. That output will now try to trigger this T2. Now the T2 will be coming into on state. It is in the conductive mode. So that's what we have written here. Whenever the T4 is on, it supplies some base current to the T2, which now conducts, and which will be acting as a current source to charge the output load. So now if it is acting as a current source, definitely what happens, the charge will flow through this one, through the emitter, and that will be here, that will be stored in the output of the capacitance. That's a load capacitance. Coming to this one, whenever the input is equal to logic 1, if input equal to logic 1, here my input that is equal to VDD, logic 1 means VDD, there's a 5 volts, your T4 is off, there's a PMOS is off. Whenever the PMOS is off, then the T2, that's the second BJT, will not be conducting. Why? Because it is not getting any kind of base current. The base, you're not supplying any base current, so that's why the T2 will be off. Whereas when coming to the T3 is in the on state. Whenever it is in the on state, it supplies some base current to the T1. Now here T1 will be conducting. If it is conducting, then definitely what happens? It will act as a current sink. Why does it act as a current sink? Because whatever the charge is stored in the capacitor at the output part, that will be completely synced to this ground terminal. It will be synced to the ground terminal means your charges will be discharged to the ground terminal. If a charges is discharging means what? Your current is flowing, that current is getting synced to the ground. Syncing of the current is taking place. That's why this particular transistor will act as a current sink transistor, and this, in the previous case, this transistor will act as a current sourcing transistor. Why? Because it is storing some kind of input at the capacitor. So we call it a current sourcing transistor. And in this case, whenever the input is equal to logic 1, the T1 is turned on because of the base current supplied from the T3. And if it is turned on, then definitely what happens? The sinking of the current takes place. So that's why we call T1 as a current sink transistor. So these are the conditions and working conditions of a CMOS inverter. Whenever the current sink takes place, and what happens? Ultimately, your output goes to 0, and that is nothing else but it is 0 volts plus saturation voltage, and that is equal to saturation voltage. That this saturation voltage will be always between these two terminals, collector and emitter of the T1. Now coming to the charging and discharging of load capacitance, we know that the charging and discharging of load capacitance is very fast because your T1 and T2 present at low impedance whenever it's turned on into saturation. Whenever your T1 and T2 are in present in the low impedance state means what? It will be having less amount of resistance. Whenever it is having less amount of resistance, it means the current flow is very fast. Whenever the current flow is fast means what? The switching of the transistors are taking very fastly. If the switching is taking very fastly, then definitely whenever these transistors are switching very fastly, the turning on of the transistors takes place. Because of the turning on of the transistor, the charge will be immediately discharged to the ground or synced to the ground, or else the charge which is stored in the charge will be sourced very fastly to the load of the capacitor. It means the sourcing of the capacitor takes place very fastly, and also the sinking of the capacitor takes place very fastly whenever these two transistors having a very low impedances. So coming to the next point here, the output levels, which is equals to this saturation region of this collector and emitter. If this is the case, if it is very small, then definitely what happens? The base emitter voltage is almost equal to 0.7 volts. If this is the case, then the base voltage is equal to 0.7 volts in case of BiCMOS inverter, and the inverter offers a very low output impedance and high input impedance. Here for this condition, you remember this one now. Whenever it is a VB is equal to 0.7, then the inverter will be having low output impedance and high input impedance. Even this is a very important objective. Whenever the transistor BJT's voltage, that is a B is equal to 0.7, then that particular transistor, here in our case it's an inverter, so inverter will be having a low output impedance will be low and input impedance will be very high. Because of that reason, it occupies very relatively small area, but still has got very high driving capability, current driving capability. And one important thing is that this inverter circuit has got high noise margins. Noise margin means definitely the BJT will be having very high noise. And since we are using the BJT in the BiCMOS structure, it will be having a high noise. And this is another structure, alternate structures for this one, alternate BiCMOS inverter. Here, constant DC supply is supplied between the T3 and T1. T3 and T1 were constant DC supply supplied. When it is supplied, then it means what? How can you say constant DC is supplied here? It means you are supplying some constant amount of base current. If you are supplying a constant amount of base current between T3 and T1, it means that your input is equal to logic 1. Why? Because until and unless this input is logic 1, the T3 will not be turned on. If T3 is turned on means then only it can supply some base current to the T1. So that's why there will be constant DC supply between the rails of T1 and T2, because it is having some current flow whenever the input is equal to logic 1. And this is not desirable arrangement. Completely, if it is completely constantly, if it is supplying some voltage over here, definitely what happens? If it is supplying constant input base current, definitely what happens? You cannot expect any kind of output at the output of the BiCMOS inverter, because the reason is that whenever the T1 is turned on, your T1 will be completely converted or transformed into current sink